All right. Well, welcome everyone. Thanks so much for joining today. This is the educator student workshop for the Mars helicopter. So we're going to be doing an activity together out of the Office of Education for the Jet Propulsion Laboratory. My name is Brandon Rodriguez, and my awesome colleague here.
Hi, everyone. My name is Lyle Tavernier. I am also with NASA's Jet Propulsion Laboratory. And as Brandon mentioned, we're going to be doing a Mars helicopter activity. So what I'm going to do is talk a little bit about what the Mars helicopter is before we get into that activity. So you may have heard that there is a rover on Mars. There are actually two driving around right now, but the most recent one, Perseverance, brought a robot friend with it. And what you're seeing on the screen right now is a picture of the Perseverance rover, and on the underside of it, this was here on Earth still, the underside of it is the Mars helicopter Ingenuity. And Ingenuity was designed to be a technology demonstration. We wanted to see if we could fly on Mars. It's something that has never been done before, and we wanted to find out if it was possible. And that's kind of a neat thing about working at a place like JPL is we have questions that can you do something that's never been done before? I don't know. Let's try it. Let's find out. But we don't just, put together a helicopter with some parts that we have lying around and send it off and hope it works. There is a years-long process where we build and we test and we make improvements to our design. So I want to show you a couple pictures and some videos here. This was sort of the original Mars helicopter design that we came up with probably 6 or 7 years ago. When we first got the idea of sending a helicopter to Mars. And the first thing we needed to do is we needed to answer a couple questions. And one of those is, can you fly on Mars? So if you take your hands and you sort of wave them in front of your face, you'll feel the air hitting you. That's the atmosphere of our planet. If you did that on Mars, you would not be able to feel anything because the air is so thin. And it's about 1% as thick as Earth's atmosphere. And that means a helicopter is going to behave differently when it flies. So we have a special room at JPL where we can change the atmospheric pressure. We can drop it down to what it would be like on Mars. We put a helicopter in there, and we had a professional drone pilot fly it around to see how a vehicle like a helicopter would behave in an environment like Mars. So got to test it out before we do it. So here's the video you can see, and here it's kind of hopping up and bouncing around a little. We were really trying in this test to fly it up into the sky, fly it up into the air and keep it in the air. But as you see, it sort of turns and drops back down. And you're going to see in the next couple of flights that really trying to fly a helicopter in a Mars-like environment is really quite difficult. And there it goes, crashed, broken. So again, we have to make sure that we do all of these tests in order to make sure that it works before we send it. So had to come up with some different designs, had to come up with some different ideas. And what I'm going to show you here is the helicopter design that was ultimately finalized for flight on Mars. And in the video I'll show you next, we're actually going through the steps of what we wanted the helicopter to do on Mars, which is start up, lift up, and do a few different movements. And you'll see those in this video that I'm about to show you. But in the instance that you saw before, someone was controlling it with a controller. In the video I'm about to show you, the helicopter itself was using sensors to detect how it was moving and adjust how its blades were positioned and how it was moving. So that was all sort of automated by the helicopter itself. So let me bring that up for you. See if I can get it to play here. There we go. So you can see the blades are starting to spin up here. So far, so good. We've got twin blades on the helicopter that rotate in opposite directions. I'm going to turn the volume down on this just a little bit. All right, so you can see here, we've got the helicopter lifting off, much, much more stable than it was in that original video. This again is the helicopter controlling itself, sensing what it's doing, how it's moving, and making adjustments in real time. So we wanted it to hover, we wanted it to turn, we wanted it to be able to move a little bit, and you'll see those things happening as this video progresses. One of the things that I really like seeing in this is in the background, you can actually see those sheets sort of fluttering a little bit. And that's from all the wind being generated by the helicopter, even though the air pressure in this room is so thin. So after it hovers, does a little move, comes back to its starting point, then of course, like all helicopters, it has to land back down. And so you'll see that in just a moment here. All right, so successful test here on Earth. But as I mentioned, we have to make sure that we do all these things properly on Earth before we send it to Mars. The real test is actually once we get to Mars. So February of 2021, so almost 2 years ago, I think on the 18th is our 2-year landiversary. We had a Mars rover and a helicopter on the surface of the red planet. And so you can see it here, it's attached still. Once we were in a place where we could set it down, we dropped the helicopter on the ground. And because when we originally sent the helicopter, we thought, you know what, we're only going to be flying this for about 5 flights. We just want to see if it works, and then we're going to say goodbye to the helicopter. So what do you do when you're going to say goodbye to somebody? Well, whoops, wrong button. You take a selfie with it. So here's the rover. It's got a robotic arm with a camera at the end of it, pointing back, looking, saying, you know, here I am on Mars with my friend, the helicopter Ingenuity. And now I'm going to step away from it. We can't have the helicopter near the rover when it's flying, because if there was something that went wrong with a flight and it crashed, we didn't want the crash to damage the rover in any way. So we backed up pretty far, over a football field's distance away from the helicopter. And you can see here the helicopter off in the distance. And this is the test of the first flight on Mars. We wanted to get that helicopter to just lift off the ground to prove that it could fly and then come back down. If you're looking closely, you can see the blades have started to spin. It's going to pop up now. It's going to hover for a moment. We're proving now that we can fly on Mars. Again, if you're looking closely, you might be able to see it just did the twist that we saw in the test chamber, and it's going to come back down to the surface. And one of the neat things about this helicopter is not only does it have the capability of flying, it also has some cameras built into it. So while it was up in the air doing its test flight, it looked down at the ground and saw its shadow, which I thought was pretty neat. And not only is it neat, but it also serves as a very, very useful tool for the scientists and engineers who are operating this rover on Mars. So it turns out that after 5 flights, the helicopter was still doing great. And we thought, well, we have this great helicopter that's doing a nice job of operating and flying, and it's giving these great pictures of the surrounding area, telling us where it might be safe to drive or perhaps too dangerous to drive if there are some big rocks or deep sand. So let's keep the rover and the helicopter kind of working together for as long as we can. And from 1 month with 5 flights, we have now gone almost 2 years with 42 different flights. So you can see here this map, kind of tough to see, but the helicopter started over here where I think you might be able to see my mouse pointer wiggling. And every little dot on this map is a landing spot where the helicopter landed and then took off to a new destination. So it has been scouting for the rover, giving us lots and lots of great information about where it's safe to travel, and really proving a lot of interesting points about flying on Mars. It's something that we can do, and it's something that we can use to help other missions. So in fact, we now have plans to send more helicopters to Mars in about a decade, later this decade, to possibly collect sample tubes that the Perseverance rover is leaving on the surface to be brought back to Earth. So pretty exciting to see the way we've gone from just designing something that we thought would work on Mars to now seeing it working and being a vital part of this mission on Mars. So with that, I'm going to turn it over to Brandon. I know you probably have a lot of questions about the helicopter, and we'll take time for those at the end. But Brandon, I know that you've got an activity related to this helicopter, so I'm going to turn it over to you.
Yeah, thanks so much, Lyle. It's it really is wild, right? I think for us, we're so fortunate to have been at JPL as this kind of wild idea was dreamed up. And as you heard Lyle mention, the idea was 5 flights, right? And that would have been a resounding success. And yet here we are, 40 some flights in and still going. And now this absolutely ludicrous idea is part of the next, series of missions to Mars. And that's kind of how this all happens, right? Is some absolutely harebrained scheme becomes the next like actual working model. So maybe we can kind of, role play that today. In the invitation for today's meeting, you probably got a link to an activity with a worksheet that looks like this. This is a cool little template for the Mars helicopter that we're going to make together. I see Lyle has his as well. If you don't have one printed out, no worries. Even just a sheet of paper, I'll walk you through. This is just nice because it shows you exactly where to cut, but I'm happy to walk you guys through step by step. So you can also see there's two helicopter models here. And that's because even though we're going to start you off by making one together, we encourage you to revise and make a second one, hopefully a better one, or at least if it's not better, you can learn why it's not and start to optimize. Just like the videos that you saw Lyle show, the first one was not the best one, right? And there's a lot of work that goes into changing little variables one by one. And I think you guys will get a chance to make improved helicopters after our first one. But let's kind of take a look together at how we can just build a base prototype. And all you need is a sheet of paper, maybe a template like this, and a pair of scissors, right? I'm going to switch my camera so that you guys can maybe see a little bit better. So I've got my template here. And what I want to do first is just cut out one of these rectangles here. And again, if you have just a sheet of paper, any rectangle will do. But let me go ahead and just cut this out. Some of you guys might get angry very early with me because you guys like to stay precisely on the lines, whereas I'm going to be a little bit more reckless with these for sure.
I am very much a cut right on the lines kind of person, Brandon, but I'll be patient with you.
Yeah, I know this is going to be, remember, it's the first one. We're just going to see how we do. So if I show you guys what I have here, should look like this. So I've got just a rectangle here. And again, if you don't have the template, it's fine. Make any rectangle you want. It could be long, skinny, short, fat, absolutely doesn't matter at all, because we don't know which is the best design yet. But what we do know is if we look at the template closely, what you can see is I've got some letters here. I've got an A, a B, X, Y, and a Z at the bottom. Yeah. I think mine is like inverted. So that's but you guys, a bit like that. There we go. Right. What I'm going to do first is I'm going to take this A and B dotted line here, and I'm just going to cut just along the dashed area, just like this. Right. So I'm not cutting all the way down. I'm just cutting a little dashed area here. And what I would encourage you guys to do is take one of these and fold them forward, flip this over, and then fold the other one backward like this. And this should give you a nice T shape as kind of the start of our helicopter, right?
Hey, Brandon, which one did you fold forward and which one did you fold backwards? Because I'm going to do the opposite.
Cool. I like that idea. I folded A backwards and B forwards.
Okay, got it. I'm doing the opposite then. All right.
Love that idea. And again, you guys as well, if you want to start kind of already tinkering with little changes, you'll notice here that this line is a little bit offset. It's not super flat, but my folds were flat. So you guys can, again, maybe Lyle and I don't have the best design by going flat. Maybe folding this at a little angle like this is better. I don't know yet, right? So if you want to fold them kind of like this on this line so that you have a little bit more of an angle, please feel free. I'm going to fold mine flat though, just like this, so that they're parallel with the rest of the body. Okay. We'll revise later if this is not so good. All right, so our next step up is that I've got these dashed lines here and here at the top of X and Y, and I'm going to cut just little slits there as well, like so, and like so. So I'm not cutting all the way across, just on that dashed line. And again, if you're working with a sheet of paper instead of the template, you can make these as wide as you want. But what I'm going to do is I'm going to fold both of these down so that I'm making another T shape. So on these solid lines here, I'm going to fold those backwards like so. Like that on one side and like this on the other side. So now I have a T shape and then I have another T shape. So I've got two T's. I'll give you guys another view of this on my other camera, just so you can see all at once. Right? Oh yeah, Lyle's looks good too. So I've got a T shape on the body and then a T shape up here on my little propellers, right? Cool. Now, the very, very last step is I've got this Z fold at the bottom, and this one I'm just going to fold up. This is going to help the body stay closed together. So it's just folded upwards against the body. This is a really nice opportunity too for later changes if you guys want to make them. We can effectively change the mass of our helicopter by taking things like a helicopter or a penny or something like that and adding that on here. That will allow it to be heavier, and we can see if that has any changes as well. But now we have a pretty nice looking helicopter prototype. So we've got, again, these guys are folded in opposite directions. These guys are folded to make a T shape, and this makes a nice little pocket if I want to change some things later. Looking pretty good. So I think the best thing for us to do is give it a first test, right? So it might be a little hard to see, but give it a little shot. I hope you guys will do the same. Oh, that one was pretty good. I got to admit, they're not always good. That one was pretty good. I noticed it caught very early. It started to spin down and didn't like drop. And it had a nice touchdown where it hit the ground right at the bottom here. It didn't like land on its side, right? So if I kind of get another look at this, pretty, not too bad. It's pretty good. Obviously, lots of room for improvement. Lyle, I think you actually had a good shot of your test, right?
Yeah, so I've got a special camera in here where I recorded in slow motion, but if you have a mobile device or a cell phone that can record slow motion videos, you can do the same thing. And so here's what mine looked like when I recorded in slow motion. I can kind of see how many times it's spinning before it hits the ground. I can maybe get a count of that. If I'm trying to improve performance, I can figure out, do I want it to spin faster or slower? What sorts of changes can I make to see that happen? And I can even see what direction it's rotating, which is a little harder to see in normal speed. And then see if there's a way that I can change that direction. Yeah, so that's kind of a nice way to visually see what's happening to your helicopter in slow motion.
Yeah, and if you are still having a hard time seeing it, even with the slow motion, you can do things like mark one of the wings. Take a Sharpie and put an X or a dot, and this will allow it to be a little easier to count those revolutions. I encourage you guys to, as you make a second helicopter, maybe you can, quantify what is better or worse. At this point, we just kind of said, hey, that looked good, but that's a little qualitative. What can we say quantitatively? What can we measure to say one design is better than the other? And you heard Lyle say, again, maybe it's the number of times it turns around. It can be the time it takes to hit the ground. So again, we can change the mass by adding some weight to the bottom here. We can change the angle of our propellers at the top. You guys can even cut them further if you like. Is square the best shape? What if it was kind of rounded at the edge, right? There's lots of options. And that's why, again, we have a second template to work with, right? So we should be able to kind of tinker around and find the best kind of helicopter that we can make. I hope you guys are able to kind of test a few designs, and again, try to get a good feel for whether or not yours is landing softly or maybe coming down a little hard, stuff like that. I see a question from a student too. Would it be better if it fell fast or slow, right? And I know that if I were on the helicopter, I would like it to fall pretty slow, but not so slow, right? Like you want to land gently, but not take forever. But I'll say, if I could make one pick for what that landing would look like, it would definitely be that I land like this, right? I know that these are, going to tip over at the end, but if you fall this way, then that helicopter is in trouble. We saw that video of what that looked like. So making sure that it lands, with the nose first is pretty important. So with that, oh, sorry, go ahead, Lau.
Oh, I was just going to say, one thing you can do if you don't have a camera to record in slow motion, you can actually take a piece of ribbon. String doesn't work because it's hard to see twists in the string, but if you take a piece of ribbon and tape it to the bottom and sort of maybe put it under your foot with no twists in it, when you let go, as the helicopter twists, it will twist the ribbon, and then you can count how many twists there are in the ribbon, and that will tell you how many times it rotated. So again, if you don't have a camera, but you've got maybe some wide ribbon or something like that, you can do that to get your count, to get that quantitative or measurable number that Brandon was talking about.
I can tell you that Lyle and I have done this activity dozens and dozens of times, and every time we see a new design that's just really, really cool. So be imaginative, right? Really, tinker around. But of course, be good scientists, right? So change one variable at a time so that you know exactly what effect each change has happened.
Yeah, I like that. If you change 12 things, you don't know what made it better, and maybe something made it worse, but got canceled out by one of the good things. So smart thinking. Well, I think we're probably, sorry, Brandon, go ahead.
Yeah, I think you're absolutely right. I think it's about time to take some questions. So if you guys want to put some questions in the chat about helicopter, Mars research, etc., we're happy to answer those for you. Although I understand if you're all still cutting and testing. And there's a question, Lyle, I don't know the answer. I don't know if you do, but Mateo is asking, how fast can the helicopter go?
Oh, how fast? I guess like in airspeed, like traveling across time. I don't know. It usually travels, I think flight 42, it flew for about 2 minutes, and it went, I think a couple hundred yards maybe. So it's not fast. It's not like racing across Mars. But yeah, not super fast. But those blades are spreading quickly. It's making a lot of thrust with those blades, so it is movable. Yeah.
Yeah,
lots of questions coming in now. Yeah,
yeah,
sorry.
Yeah. The speed of the rotation of the blades is really where you're getting high velocities, because as Lyle mentioned, because the atmosphere is so thin, a normal rotational speed you would use for a helicopter doesn't cut it. You really need to spin very, very, very fast to be able to make this happen. And kind of similarly to the question about what is the rover made out of, it also needs to be incredibly, incredibly light. So it's a lot of, like carbon nanomaterial, something that's strong, but very, 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 very light, low mass, because lifting heavy things is very, very difficult to do when there's such a thin atmosphere.
All right. I see a question that I kind of like. Would this spin in space? And the answer is yes, it would spin, but because there is no air in space for the blades to push on, it wouldn't fly. It would just sort of move there, and the blades would spin, and nothing would happen. So if you took this to the moon, it would just sit on the surface and not fly, because there's no atmosphere on the moon. That's a neat question. I don't think I've gotten that question before.
I see one about actual testing in the classroom too, which is exciting. So Brooklyn says when they compared the helicopter with a coin and without a coin, the one with the coin fell faster. Is that good or bad? I don't know. As I think your experiment is super valuable, and I think you found the right result. I think it should fall faster. I would encourage you to check the number of revolutions too. So did it spin as many times, more times, or less times as it fell down to the ground? But as long as it lands, somewhat softly, I think you're in good shape. But it is interesting to see how little changes can affect the landing.
Yeah, and I think that's kind of an important question to think about too, because when we're sending things to Mars, the more things we send, the heavier it's going to be. So if you've got, a helicopter carrying more mass, we've got to know that it's going to be affected by that. So good observation. Here's a question that I thought was kind of interesting. How big is it? Because we only showed it by itself on Mars or next to the rover. And if you don't know how big the rover is, there's no way to really tell how big it is. So I'm going to step back a little bit. And the helicopter wings are about this long, about a meter, a little more than a yard wide. And it's probably this tall. So it's not very big, and it only weighs a couple pounds. It can't be very heavy because we've got to be able to lift off the ground. And if it's too heavy in that thin Mars air, it's not going to be able to fly. So that's a nice question I saw.
Yeah. I see a couple questions too about effectively how long it took to make, which is, I think really important for students to understand. I try to communicate this to all young people interested in science. Years. It took years to make because this is a completely new idea. This is, take the Perseverance rover, for example. This was the next evolution of the Curiosity rover, a much updated version, but we kind of already had the blueprint. So even though Perseverance is advanced, that took years, but the helicopter had never been done before. We had nothing to go off of. We've never attempted anything like this. So even just this small little, several pound device hopping around Mars took an incredible amount of testing and just kind of new data collection and new exploration to be able to happen. So I mention this because some people who want to be scientists in the future really love that. They really love the idea of just getting like deep into this one topic and making it work. Whereas some people say, how do they work on the same thing for so many years? So science comes in all kind of shapes and sizes. You can work on one project forever to optimize this perfect new thing, or you can work on several projects for less time and kind of do little bits and pieces you like. So if you're into really taking a project from 0 to 100, the helicopter is your path. If you're interested in like instruments and rovers and things like that, then we have paths for you at NASA as well.
So I saw two interesting questions, and they're not exactly the same, but they're kind of related. One asks, if the helicopter had bigger blades, could it lift more mass or more things? And the other question was, if the blade spun faster, could it travel faster? And so this is kind of an interesting thing that the engineers had to figure out, is because those blades are spinning. Well, let me back up. Because the air on Mars is so thin, the blades have to spin faster than a helicopter on Earth. A helicopter on Earth, the blades spin a few hundred times per minute. On Mars, they're spinning over 2,000 times per minute. So they're going very, very fast. And when they're going that fast, one of the things that the engineers had to be worried about is that the ends of the blades could be going so fast that they could break the speed of sound. And if they break the speed of sound, you get a sonic boom and a shock wave that could damage the rover. So if you get longer blades, they'll be going around even faster at the tips. So that could break the speed of sound and be a problem. If you spun them faster, even the same size, they could break the speed of sound. And so that would be a problem. So we're kind of at a sweet spot for the length and the speed of these blades for how much we're able to carry. So kind of a neat combo of two questions from two different people today. So thanks for those questions.
There's another question here about how we actually fly the helicopter as well, right? And I mean, of course, this is really important for people to understand as well, because of the distance in between Earth and Mars and the time it takes for light, for a signal to get in between the two. You effectively can't fly this in real time. There's no joystick situation here where there's a pilot. And you heard Lyle mention that, when we tried to have a person flying it, it doesn't work out so well. So having sensors was actually a more effective process. So the answer for how we actually fly it is with computer science, with coding. So we send a program, we send a list of operations for the helicopter to complete that gets transmitted from us here to Mars. And then that code gets executed by the helicopter when it's ready to perform its flight. So we don't actually get to see it in real time. We don't control it in real time, but we tell it to execute a command, a list of sequences, and then it will do it. And then we get that data back later, right? So that delay is actually very, very complicated, right? It really throws a wrench in being able to do all the kind of research you want to do, because you sit and wait and you hope to get the good news later on. But computer science is the answer, guys. It really is. All things get done in Mars research with computer science.
So I saw a question here that I think is kind of an interesting one, because you, Brandon, talked about how long it takes. Someone asks how many engineers worked on this helicopter, which is such an important question. And I've got a picture of the helicopter team that I'll put up on the screen so you can see it is not just a single person who works on this, and it's not even just 2 or 3 people. It is a very, very complex machine. And so there are lots and lots of people who are working on this helicopter. And this probably includes people who, as Brandon mentioned, maybe worked on it for a little bit of time and then left to work on something else, and they weren't here for this picture, or maybe they were even sick that day and didn't get to come in for the picture. But many, many dozens of people worked on this team to make it a possibility.
We probably have time for 1 or 2 more questions. I know that some people are asking, effectively what happens if something goes wrong, and of course, what happens if it lands sideways? What if it stops working? And of course, how long does it stay there? And the answers are kind of all the same. The Mars helicopter does not come back. There's no technology yet to bring things from Mars back to Earth. So remember that, again, our goal was 5 flights, which we've already blown out of the water. So eventually, it's true, at some point the Mars helicopter will stop functioning, although we hope that we can continue to get all these awesome results from it. But when it does, it'll stay there, just like the rovers before it, like Spirit and Opportunity have in the past. And this is simply until we have the technology to bring things back, we end up kind of leaving our robotic footprints there on Mars.
All right. Well, there's one more question I don't have the answer to, but I kind of want to bring it up. And someone asked how many women worked on this. And I don't know the answer, but I do know that the lead engineer was a woman named Mimi Ong, and she was just awesome as far as bringing this project to completion.
Yeah, we should point out, our good friends, Terrell Bailey, Farah Alibay, not only women, but female minorities have really actually been the drivers for much of the helicopter project.
Great questions. Well, Brandon, I think we're probably just about out of time. So I want to say thanks to everyone for all of your great questions today. We got a lot, and unfortunately, we just don't have time to answer all of them, but really appreciate you taking the time. And Brandon, thanks so much for the activity. I'll let you say anything else you want to say.
Yeah, same as Lyle. I always really appreciate you guys dialing in. I hope you guys enjoyed the activity and came up with some really cool prototypes. Remember, we do these monthly, so if you liked this activity, if you or your students want to come back and do this again, we'll have a new event posted soon. Keep an eye on the JPL Education webpage, and we'll get you guys registered for another. So thanks so much. Really appreciate you attending. Take care, everyone.